escaped Sapiens.
Our planet is covered with all sorts of life, and we have a pretty solid understanding of the evolutionary processes that led to all of its complexity. But evolution doesn't tell us anything about how life began in the first place. So how did it begin? Did it only occur once, and is it likely to happen elsewhere in the universe? In this episode of the Escape Sapiens podcast, I speak with Cronin, who is the Regius Chair of Chemistry at the University of Glasgow in the UK. Lee is attempting to create artificial life in the laboratory by searching for sequences of chemical reactions that are able to retain information and build up complexity at each step. In other words, he's attempting to go from basic chemistry to the sort of complexity that might be thought of as some form of artificial proto-life. If successful, Lee's work has the potential to tell us about the kind of processes that may have led to the origins of life on our own planet. I hope you enjoy hearing what he has to say. How did you first get interested in the origins of life, or the potential mechanisms behind the origins of life? And the reason why I ask is because this is one of these great questions that in overview a child can understand, but which has extraordinarily deep science. So I'm wondering if you grew up being interested, or this is something that evolved through your research.
I guess I've always been interested since I can remember walking on the beach, I've always wondered what my reality is, and that's been extended through various means, and in terms of what I understood that the world was, So I guess I'm just trying to think about what it was. There really like one day when I woke up and said, "Oh, I've got to try and make an artificial life form and find." For me, I used to spend a lot of time. Kind of outdoors, I used to spend a lot of time playing around with things, be it outdoors, in a small workshop, and just looking at stuff and wanting to understand the mechanism by which that stuff had come about. And I was always kind of obsessed with I love technology since I was I was a gadget freak since at least 9 years old, if not younger. Love what we could actually do. But then I'm kind of obsessing of what knowledge do I need to have to recreate that technology? So I was really interested in the chain of events that kind of got from, I suppose, let's take Homo sapiens coming out of Africa, for us suddenly becoming agricultural, and then basically developing technologies and making that stepping stone to where we have, nanoscale electronics now, and control over information and matter and sensing modalities that we never had before. And so for me, understanding the origin of life is an extension of understanding the origin of our technology. Mm-hmm. And I think that's, for me, a really important set of questions. And I would love to be able to recreate it. And I wasn't really thinking about aliens and going to Mars. I don't particularly have going to Mars on my agenda. But maybe, recreating my environment, what would I need to do? Maybe I'm too much of an Englander, right? I'm living on an island. If I go to a desert island, what are the minimal things I need to take with me to that island so I can have a life that I like having, in terms of recreating everything I need: drugs, computation, or facilities, a warm place to sleep, stuff like that.
Mm. Speaking about the chain of events that led up to our current technology, in our cultural context that we sort of live in, when you think of the origin of life, it's easy to think of it as being some sort of on-off switch, but this is absolutely not the current scientific consensus, right? I should think of it more like an evolutionary process where there was not necessarily any distinct boundary between what we would view as being alive and, I guess, not alive. Is that the case?
It depends which culture you come from, what tradition and what subject. So I think the chemists think that origin of life is their problem to own, and a lot of them think the origin of life is magic, which is kind of annoying, right? Because chemistry is not magic, chemistry is scientific. But what I think they're saying is that the origin of life was a very hard thing to have happened. But that, I think, it displays a failure of imagination. Whereas I think the physicists who have to, and also it's not a problem with the chemists, it's just the way the subject is taught. Whereas I think if you're an astrophysicist, you've had to be a magician for a lot longer, or a cosmologist maybe, right? And so it's easy to imagine that there must be some continuum and there should be life elsewhere. But I mean, most people say, look, it's interesting. We have seen no evidence of life elsewhere. We haven't seen evidence against it. We just haven't seen evidence for it. And we don't really understand life itself. I think that's my point, is that I think the problem about defining the origin of life or thinking about it, we can't even define life. Mm-hmm. So a lot of chemists think the origin of life is kind of obvious and simple, and some think it's really hard and impossible. And the physicists are kind of saying, oh, of course it happened because physics is everywhere. And all those viewpoints are basically not wrong, but they lack evidence and a coherent framework on which we can have a discussion. So what I'm trying to do is to start again and say, look, why don't we just actually reframe the argument and have a discussion and gather some evidence and come up with some theories and test them. We need anomaly, we need evidence, anomaly and theory, probably in that order, but I don't mind starting with a bit of theory, a bit of anomaly and a bit of evidence, but take your pick. I think you could see life as an anomaly. So what I mean is you look at the stuff on Earth and it's moving around, right? It seems to have inbuilt agency. And rocks don't walk around, but snails do. But snails look a bit like rocks, they can move. So it's like, which is the anomaly here? Is it the snail or the rock? Mm-hmm. I mean, for you, the rock could be the anomaly because it's not moving. If you're on an island full of snails, you're like, gee, why is that rock not moving? All the rest are. So I think it's kind of defining your anomaly and then doing experiment and gathering evidence against that and trying to really be honest about the experimental process and design process.
So with the experiments that you have done in mind, is where do you sit on this fence? Is the origin of life something that's continuous and happening today, or is it something that really depended on those initial conditions that were in place 3.5 billion years ago, 4.5 billion years ago? Is it some special event that that's rare, or is it something that is rather commonplace?
I mean, I just don't have. So if I'm going to be a lawyer, and I don't like being a lawyer, but being a lawyer is fun for a bit now and then. If I was being a lawyer, I would say I do not have any evidence that really says the origin of life was special, but I don't have any evidence saying it wasn't. But as a naturalist, I can see chemistry everywhere and biology everywhere, and I can see physics in operation. What I would like to do is assume that there doesn't seem to be anything mystical. I don't find when I dissect a living thing, it's contained of atoms. If I was to take, I don't know, let's say a bacteria rather than an ant or a mouse or something, and put it through an atom grind and grind up all the molecules into atoms, and then I got a bunch of dead atoms and put them together, they would be indistinguishable. So the fact I can get a life form and break it into constituent building blocks, which I can find in a dead in a laboratory or create under laboratory conditions where they wouldn't be alive, I would say, well, that's really interesting because the atoms coming from the living thing and the atoms from the dead thing I've now made indistinguishable. What is different about the two things before I put them into the molecular grinder into their atoms? So I think the origin of life is probably asking about the origin of life is perhaps the wrong question because it's very historical. It's worth asking in one framework, but I want to know what does happen rather than ask what did happen. And so if you were going to say, well, come on, just give me what do you think? And say, well, I think the origin of life is a continuum event. It's happening everywhere. I don't think there's anything special about it. I think there might have been something interesting at the stage that Earth has gone through that may have confined the origin of life on Earth to certain stages, and that's why we don't see it going on now. And also because we're the dominant technology on Earth, or the dominant self-sustaining technology on Earth, that we probably we're not able to recreate it easily or observe it in the environment because we just don't know what happened. And I think that where I come at is I think that the origin of life or making a life form from scratch is solvable. It doesn't need billions of years, but there is some fundamental conceptual problems about physics and chemistry and then by consequence biology that we need to solve. So for me, this is like all my Christmases have come at once. It's like the most exciting and interesting research topic you can imagine. But sadly, to go with it, it seems to be very full of a lot of opinion and dogma and precious evidence. And I'm a scientist. I don't deal with opinion unless you can turn... an opinion into an experiment or a
So
theory that I can test experimentally.
So if this is a process that is ongoing, is your idea that, so it sounds like your idea is that the current species, the current technology, in your words, are out competing, or is it that we don't recognize the process happening because we wouldn't know what the beginnings of the process look like?
Both.
They're so far removed from cells.
I would say both. I would say that, the process that gives rise to life, or eventually life, is everywhere, but it's very primitive. And I think when it starts to make its own way to a evolutionary dynamic of some description, a technology, that basically life on Earth is established in a particular state, and the solution we have on Earth is one of several solutions. And I think it might be quite hard for many solutions to coexist, because there's a great deal of benefit you get from sharing the ribosome, sharing DNA, sharing that technology, because what you do is you share evolutionary experience on Earth. If the sole purpose of life is just to exist, then it makes sense that you share a common framework, because you can learn from everyone's mistakes and successes. Mm-hmm. So the things that die and failed are no longer in the lineage. The things that survive are in the lineage. And because you're built on the same kind of technology, you benefit from that directly.
Mm-hmm. And so this would be sort of an explanation for why it seems like everything on Earth derived from a common ancestor, I suppose.
Yeah, and I mean, I think probably it was a gradual process. I think there were many origins of life on Earth going on at the same time. There are many competing, let's say, technologies or instantiations of biology, of evolution going on. And there was the things that won, obviously, were the ones that could persist in the environment at the time it was emerging. And here's where I'm kind of fascinated about with this kind of idea of doing just enough to survive to get to the next step, because human technology, in a way, might be just seen another extension of that. We've done just enough to get access to energy from fossil fuels, and hopefully we need to do just enough to prevent catastrophic climate change to continue on as a species, and maybe rewild the Earth, or whatever we need to do. Mm-hmm. If we think that for the preservation of life on Earth and biology, we need to do some other things. But I think that's so. I think that maybe some aspects of what we see in biology now have some relationship back to what Earth was like, and that's why the origin of life idea, the historical experiment, does have merit. But I believe it's mostly an illusion.
I suppose it's not such a silly question to ask, because you can imagine a situation where we wipe ourselves out, or we replace ourselves with some artificial intelligence that many millions of years in the future looks back to their own origin, and we'll have trouble, finding a biological origin to an abiological life. But
exactly.
Okay. In terms of what we do know, then, what is the earliest evidence we have? What is the most primitive life that we have evidence for? And
I mean, I'm have to show I'm not a very good archaeologist or there are lots of different archaea and cyanobacteria, and some very early indications of very primitive bacterial or things that come on that tree of life. I guess you have the archaea and the bacteria and all of this. So there seems to be a evidence of systems that had cells, if you like, the first cellular objects going back. I think if Earth is about, I can't remember, it's either 3.8 or 4.2 billion years old, round about that time. And within a few 100 million years of Earth forming, around about the time of the late heavy bombardment, there was evidence that life sprung up pretty quickly with that or after that. So life, some people thought that life took 1 billion years to get going, but that number has been constantly pushed further and further back. So I think that, life really got going super quick within, millions of years, not hundreds of millions of years, maybe even hundreds of thousands of years. And all that happened was because there was such a maelstrom of activity that every now and then, a big boulder would come in and sterilize the planet, and we go, oh, we need to start again. It's a bit like when you're writing a document and you keep losing it, and you remember the story slightly so that the story changes. And I guess that happened a lot. And I think that there's maybe a way of actually kind of digging into that.
I guess what I was trying to get at is, is the evidence based on, for example, chemical changes in the atmosphere, or do we actually have, a fossil where you can go and see these microscopic dots that we presume are the result of bacterium?
So there's lots of arguments about these nanofossils, but the problem with them is we don't know if they were formed by because we don't know what life is or what the signatures of life really look like. We don't even know what life is today. We know what life isn't, and it's quite difficult. If you ask a biologist to define life, they'll be a bit confused. They'll say, "Oh, it's things that have a ribosome and this, that, and the other." But is that really life? That's just it's like trying to say a computer and saying like, "Oh, a computer is a." It's got let's go back to one of the Apple Macs. It's got this, and it's got an apple on it, and a rainbow, and that's not a computer. That's a Macintosh, or But there is microscopic evidence, or there are artifacts that people found that date back to that length of time in the past, and that seem to have properties consistent with them being extinct life forms. And and there's lots of argument about whether they are or not. I would love to find examples where we could get the earliest DNA. I don't know what's the oldest piece of DNA that we know. And I'd also like to actually find life that basically, is there life on Earth that has been cut off from the rest of the world for the last 3.7, whatever billion years? And we could see how that was evolved, because if that environment hasn't changed very much, it might be that life form might be very similar to the life form that came out of the primordial soup.
I guess one location you might find that sort of information is if there's been a meteorite impact that spewed life forms out into space, and we find it on Mars or some other planet or the moon or somewhere down the track. But on Earth, I suppose we've looked. I guess deep in the ocean is
I
one
think
location.
under the ice sheet in Antarctica, I think there's so much to be found there, and I think there's a lot to be found at the bottom of the ocean and underground. But the problem is that life gets everywhere, right? Life is everywhere on Earth, and it's pretty good at adapting and reinventing itself. So I wouldn't be surprised if we find alternative life forms on Earth. But they would have to be under very special circumstances, trapped from the rest of the planet, because not to be assimilated into the evolutionary dynamic. Because why wouldn't you? Why wouldn't you share information and learn from other? That's what evolution's brilliant at. Really, at the top level, all life is the ability for matter to make itself more improve its properties of existence, and it's not just being stationary like a rock. So it's got more than existence, but there is, it's able to kind of maximize the heat death of the universe. Basically, the living universes will die faster because they're going to create more entropy.
Well, that was the recent paper, the physics paper from a couple of years back, right? That DNA is the most efficient user of solar energy or something like this.
Yeah, but that was nonsense. I mean, the papers like that that just say the problem is that, I don't know the paper in question in detail. When people make statements like that, it's very difficult because you can't do the counterfactuals, right? But you can just make the observation and say, hey, compared to a lot of other things, DNA is really good at this, but with respect to what? The most efficient solar harvester out there is a silicon solar panel. So you can get 30% of triple, junction silicon solar cell, 30% efficiency.
But they're not self-replicating. I guess the other physics argument is, as you're saying, that organisms rapidly increase entropy, the heat death argument. But
Well, what organisms do is they are able to do work with the sun's energy, right? What we've done is we've had billions of years of the sun giving us this free energy, and we have used it. By golly, we have used it, and it's great. I mean, it's like, and I think that's the planet's had a lot of fun.
So in terms of actually, fabricating life from scratch, the obvious place to start looking is at a cell, but cells are really complicated. I was doing a little bit of research, or I was looking into my old high school level biology, and cells are incredibly complicated with all different structure. We've never recreated anything similar. I mean, before your research, no one has ever created anything close to a cell, right?
Oh, lots of people have tried to make cells. So I think I've done, let's go ask that question. Cells are incredibly complicated now, but were cells complicated at the beginning? Because cells are a minimum self, aren't they? Do molecules evolve? No. Do cells evolve? Kinda, but cells evolve in populations. I like to say to people when I'm making jokes at parties, it's like you evolve together, you die alone. And what I mean by that is like kind of brutal, but I mean is that we evolve in a population. So, but to evolve in a population, we have to have a self, an inside and outside, and cells are really good ways of doing that. So the very first cells might have been the same stuff, everything, right? Just salad dressing, or literally oil in water, or whatever. And then after they accumulate stuff from the environment, one group becomes better than the other group at surviving. And then machines are invented. Maybe machines are distributed between the cells, and they get compacted, and they get evolved and selected upon. And I think that's the fact that cells are now really sophisticated. You should view like a kind of a technological development. That you basically, each cell has now got its own power source. Each cell has now got its own kind of way of moving in the environment, and exchanging information with the environment. But it didn't need to always be that way. You could have had a network of objects that were dead individually, but that network was able to self-sustain, where maybe you might have one cell in the object dedicated to doing one reaction, and another cell dedicated to recording some information, and another cell dedicated to something else. And because their logistics was so good, and they hadn't undergone Brexit, that they were able to kind of be a cohesive entity. But the problem when you have a network of objects, they're fragile, they're not robust. And so if that was broken apart, the living nature of the network would be killed or stopped. So basically what you wanted to be able to do is recreate that again when the cells got together, and over time you'd have this get together as a network, be more functional, get broken apart, not be functional, and then to basically, if you lived in some parts of the US where there's tornadoes all the time, you have a generator in your basement, right? Because the power's always going down. And so you have to become a bit more independent. So I think that the first cells were incredibly simple. And what we've been doing in my lab is not trying to create a biological cell, but say, hey, let's have a lump of stuff and let's put it through an evolutionary selection engine. And let's see what happens. And let's put it through cycles of evolution and watch it become more sophisticated and independent.
So I want to jump into that in a second, but I just had one or two questions before we go specifically to, I guess you're working with salts and all sorts of chemistry, but have researchers taken very simple cells then and removed pieces to try to build the most simple cell they can? How far can we go there?
So there's a whole area of science called synthetic biology, where people have been, who understand molecular biology very well, are able to build different types of systems that are extremely good at, translating DNA and building proteins and so on. But the problem is all these systems are actually dead. They don't replicate without some help. So people have made quite advanced synthetic cells that can do some function, express some protein, but actually, when it comes down to it, they are not able to leave home. They are the proverbial teenager.
Mm-hmm. I see. But so in terms of the components that make up a cell, in the lab we're able to synthesize amino acids, lipids, like every bit of the chemistry we can do in the lab, right?
Yeah, and you could make every. It's very easy to. Well, very easy. It is possible in principle. There we go. There's always when people says that to you, you have to put on the alarm. It's possible in principle. Okay, it's possible in principle to synthesize every molecule that's in a cell, from the cell wall all the way up. Why would you? I mean, some of them are very simple. You can get them from the environment. But when you put them all together, they don't boot up. Mm-hmm. What Venter has made a life form, but when he did it, he cheated slightly in that he synthesized the DNA and he put the DNA into an existing minimal cell system and showed that it would minimally turn over. But that's not the same thing as synthesizing everything, putting it together. So there's still this spark of life. So the thing that Venter used can be traced back to Luca all the way back, right? He didn't actually synthesize a cell from scratch. So that means there's some hidden information in the living cell that we know that is responsible for how it works, and we just don't know. And that, for me, is one of the most exciting mysteries of molecular biology that molecular biologists won't own up to. That molecular biologists do not know how a cell turns over. They have theories, but if they knew, they'd be able to build one from scratch and put all the parts in and it will work. It doesn't work.
I'm actually not familiar with this result from Venter. So he or she took made a carbon copy of DNA using...
Yeah, so what Craig Venter did, so it's a he, he's a very great entrepreneurial pioneer and a great molecular biologist. Not a scientist, an entrepreneur, but very good technology. I feel he's could be a great scientist, but chose to... He was in competition with the Human Genome Project, right? He was the company was trying to get there before. So what he did is he took a simple parasite and he copied all the DNA in that parasite and sequenced it all. And then he went to a gene synthesis system and he made all the genes robotically, okay? And then added them all together robotically, and then put and then took a cell, removed the natural DNA, and put in the unnatural DNA to see if it worked, and it did.
That's still amazing. I mean, that's...
Oh yeah, absolutely amazing. But of course, if I take a hard disk out of the computer and put it into another one, of course it's going to boot up. But the thing is, technologically. But but what I've got now is if I take an existing native computer and copy all the bits and take my hard disk and put it in, it doesn't work. That means we don't know what's going on with the metabolism, the lipids, the molecular structures, the way the translation occurs. There's some missing ingredients in the cell that we haven't yet got to the bottom of, because the dogma of biology, the central dogma, is not all the story. We know where the information is stored that evolution preys on mostly, but we don't know where it's all stored. There is hidden instructions in the cell, and that's kind of a heretical statement, right? But it must be true, because if it wasn't true, we would be able to take the information that we have about the cell and boot it up. And some people might say, "Oh, we've been able to do that. We just haven't done it very well." And I'm like, well. Yeah, maybe, but that's one interpretation. But what seems to right now is there is information missing from theory missing, some principle missing, or sorry, not missing, but we just don't understand, and therefore we're not able to implement it artificially, and therefore make a competent living cell.
But is it the case that we're missing some information, or that just technically it's really, really, really difficult to build a cell? I mean...
Well, yeah, I mean, you could say that. Again, if I was being a lawyer, I'd have to agree it might just be very difficult. But people have tried for a very long time and they don't seem to be getting very close. I mean, the cells don't replicate.
I see. So, yeah. But so in terms of experiments, starting from Miller Urey all the way up to today, what do you bring to the table? What have your experiments done that's new? What's the new hypothesis? What's the...
Sorry, 1 second. So what's the hypothesis? What are we bringing that's new to the table? Well, I think what we're bringing is a number of key ideas. The first one is that we are aiming to try and understand how life could start in the lab now if we would start again. So we're basically saying, hey, let's treat this as a testable problem, not a historical problem. And in terms of, let's not try and work out what happened way back when and recreate that in the lab and hope for life to come out. Let's instead try and say, well, what does life look like now? Why does life look interesting? What can we do to try and get something evolving? So that's the first point. The second point is to kind of view the problem of making a life form as not as something that needs literally billions of years of evolution that we could do quickly. And the other thing is this recognition that evolution is a force, if you like, or this is a hypothesis that I want to prove. I have some evidence that the Darwinian evolution, not just time evolution, and that is selection of stuff in the environment at the expense of other stuff. So there's limited resource, and there's selection that goes on, and something wins or something loses, so live and die, occurs even without biology. So I'll say that again. The Darwinian evolution proceeds in reality even without biology. And all that you see, all biology is an amplifier. It's just biology is able to evolve much faster than other materials. So that's, I think, our key thesis, that we want to see how does normal stuff evolve, what makes it evolve, what turns something to become evolutionary, and then try and replicate that process in the laboratory and watch the process of evolution generating information in real time, evolutionary time.
Mm-hmm. So what are the models that you're looking at then?
In terms of theoretical models or physical models?
Well, both. I'm actually interested in how you actually do the experiment. But so, what are the objects you're dealing with? What are the what holds the DNA or the
Well, we're going all the way back, so we're not making any assumptions about DNA or proteins. I think the DNA and proteins and the stuff we have in the cell right now is simply too complex to have merged from scratch. And so, if what we need to see, the first hypothesis is that life that we have now isn't the first life. There's other life that kind of came before it. And so, our starting point is that we're doing this in chemistry, okay? Because it's easy to manipulate atoms and molecules in the lab. And what we're trying to do is to say, how can we do chemical reactions in an environment, and how does that such that the environment is able to act on the chemical reactions and cause them to start to evolve. Mm-hmm. So can the environment act on some chemistry that's going on, and let's just say we're going to do it in a test tube, so test tube evolution, and say, right, how does the chemistry get constrained by the test tube? Maybe in the test tube we put some rocks, maybe we put some fire, maybe we put some lightning, maybe we shake it, maybe we do something specific to it, or an electric field near a black hole, whatever you want. And then we do the chemistry, and then we measure what's going on. And that's what we're starting to do, is to build a series of what I call evolutionary difference engines. And what does that mean? It means, well, evolution is about change and adaptation and selection. What we need is basically two different rates of change, where the chemistry in the test tube changes faster than the chemistry on the outside, so the chemistry in the test tube can survive in the environment, come what may. And survive means persist for a certain length of time.
I see. So I might not understand correctly. So you have some chemistry that's occurring in a test tube, and you're looking into what you mean by evolution is, so I have some chemical reaction that then makes some other chemical reaction more likely to happen, and then I get some sequence of chemical reactions that occur. Is that what's happening?
No, I can give you a much more concrete example. It's really hard what we're talking about here, because we're talking about something that's pre-paradigmatic. So what I mean by that, a very dramatic statement. In a lot of sciences, when people were struggling to understand what something is, there's lots of competing theories and feelings and intuitions, and those intuitions get encoded in some language that's imprecise because the theory's not there yet. So what I did is I went back to the basics and said, what is the difference between the chemistry of biology and the chemistry that's not in biology? And its simple answer is that chemistry in biology has a history. The chemical reactions are controlled by what happened in the past, by selection. So all that biology is chemistry of history. So it's like, aha. At the beginning, there is no way of storing the information. The history is just really kind of, an unwashed plate. It's like, you could basically, let's say you take a frying pan and you cook something, and at the end you clean the frying pan and it's clean and go again. But let's just say you make an omelette in your frying pan and it's nice and clean, and in the end you leave the residue, and then you make, a waffle, or you make something else, and each time you make something else, it will be affected.
Like food poisoning.
It will be affected by the thing. Well, the chemistry will be affected by what's in the pan before. And it doesn't have to be to a huge event. You can have an amplification through some catalysis. And so I think what is interesting is that the history is recorded in the system, not very efficiently, but efficiently enough for the past to affect the future. So, as soon as we have a system where the past can affect the future, you invent time. You invent biological time. And that's the problem, right? The physicists coming to terms with. Physicists are completely screwed up with their notion of time and evolution in the universe. So they're basically misleading all the chemists. The chemists don't have the mathematical nous to really untangle it, and the biologists just don't care. Because the biologists are like, we have it working. We don't care. Why do we want to know where we came from? I'm quite happy making proteins and curing disease and making vaccines that hopefully will get rid of COVID-19 and stuff like that. So there is this really interesting disconnect because the physicists really like to be up at the beginning of answering these creation stories.
So in the experiments that you actually do, how will you know that you've done it? Then what's the smoking gun of what will win you the prize, or what will send you to Stockholm?
I think so. I mean, well, let's let other people worry about prizes. I would like, obviously, to do something that everyone would recognise as terribly important and exciting. I think that comes, But yeah, okay. But let's just say in everyone's eyes, it's a Nobel Prize is a good indicator of success. But I would not accept I should say here, you should not accept a Nobel Prize for anything less than kind of making a life form, not convincing a narrative, right? Lots of narratives competing for prizes out there. And I don't care about narrative. I want to know what happened, not I don't want to know what story you want to tell me. So what I think that needs is literally, I need to be able to turn sand into cells. So I need to go inorganic stuff in my machine, and I need to audit what happens, because when I make the machine, everyone's going to say, "But you're cheating," and I'm like, I've always wanted to be a god. I get to be a god. I'm making my own life form. That's the only way I'm going to get people worshipping me. I mean, I'm joking, right? I'm joking about the god complex. But what I'm not joking about is the problem that if we manage to create a life form in the laboratory using a machine that we build, everyone's going to say, "Oh, well, maybe well done, but you made the machine, or you made the machine. Where did you come from?" That's really... So what we've got to be very careful to do is to basically explore chemical space and inorganic chemical space to see how life got started and that memory got created, and show the constraints for that can occur on Mars, on Venus, on Earth, wherever. And that the absolute inputs we needed, all that we did in the lab, probably was to accelerate that process because we didn't have a billion years. Okay? And
I think it's okay to go in baby steps and start with having a lab. I mean, I think it's okay if you're present.
Sure.
For the first.
but Craig Venter will say, "Look, I've already made a new life form."
Mm-hmm. Sure.
And he did. He took the DNA. Well, he didn't entirely do it. He did something very close. He already made the world's first synthetic life form.
I see. So you want something that's actually plausible. But so okay. So what have you done in the lab? So in terms of the actual experiment, when you get down to it, you put the white jacket, the coat on, and what have you done?
So we've done. So what I had to do to create this is I needed to solve this problem. I needed to kind of take the approach that CERN, or actually particle physicists, took to looking for the Higgs boson and getting all the particles sorted out. The problem we have with the origin of life is nobody knows when we've done it. What is the origin of life, right? You either made you either make a fully functioning cell, or you've done nothing, or you made a bit of RNA, or you've done nothing, and even if you've made an RNA, you might have cheated. So what I was saying is that I need to develop a new kind of theory, so the basic theory is that matter evolves, and matter evolves. We should be able to tell evolved matter from unevolved matter with a simple test. So you have theory, test you can turn into experiment or measurement. Like the Higgs boson, you needed the Atlas detector to detect the particles colliding and looking for the anomaly at the right energy range. So you have theory, you have metric, you then have an experiment, and you have a model. So what you do is you have your theory, and that theory says, I'm going to make a model. That roughly I'm going to look for this type of behavior, this type of change of complexity, or this amount of information processing. So we've made that theory. We have a theory that can tell the difference between molecules that are made by a living system or molecules that are made in a random environment. Dust. Great. So now that theory is about related to life. We can put that into a simulator and work out how much we need to do. So we've now literally made a series of robots, if you like, or not if you like, they are robots. They are chemical robots that put random mixtures of inorganic materials into a test tube, shake it for a bit, do a reaction, heat it up, then cool it down, remove 99% of it, keep 1%, that's the seed, that's the memory, what happened before. Do exactly the same reaction again. Then stop, throw away 99%, well, it's actually 90%, we keep 10%, but 1% sounds more grand. In the end, it should be 1%, right? So you keep a seed. So each time you do an experiment, you do an experiment in a fresh flask. Beautiful, works, lovely. You then measure what happens. You look at the complexity or the information in the molecules. Should be not very much. You then throw away most of the chemistry, but you keep a little bit of a memory of what happened. You do it again. You keep going in a cycle, in a cycle, in a cycle. And what we're looking for is the ability for the system to start processing information. And of course, we have all these control reactions going on. We're comparing. So we're literally, people talk about monkeys on typewriters writing Shakespeare or something. We're trying to build the typewriter and the monkey and the Shakespeare at the same time. Because when people talk about the probability, when creationists say life is impossible because you need a monkey on a typewriter, they're misunderstanding the typewriter and the monkey and the Shakespeare was really simple at the beginning. It took small steps. So it was like just basically, if you've only got 3 letters, it's easy to produce the in the end, right? It's like, the, and off you go. And then when you've got then the opens up another door where you can maybe the big, and then you might get to brown, fox or whatever, and so that's what we're doing in the lab right now. So we've built the system, we have the model, we have the theory, and we have the metric. And just like the physicists went look for the Higgs, we are now going looking for the system that gives a jump in evolved complexity from nothing. And we're using a technique called mass spectrometry to get there.
So the complexity is the length of some polymer, or what is the in terms of the chemistry, what is the complexity that you're looking for?
So we're not thinking about it. May be that polymers do this, but what we're looking for, and this is why it's really hard, and most people disagree with me, but they are all wrong. This is the one thing in my life I'm right on, and that's because I believe in the second law, and I don't believe in magic. So what I mean is, so basically, if you take this watch, it's got a lot of parts. Okay, it's a titanium watch. If I type on the screen, it's a Garmin actually with a solar panel in it, lots of parts. So this watch couldn't have assembled itself. It was designed by someone. It was made. It has enough bits in it. If I give you a lump of dirt, the same mass of a watch, you would instantly tell the difference because you would see that the matter in the watch had to be constrained in a non-natural way. So what we have done is we've made a way of measuring that, and what we have found is that molecules there are some molecules that can't appear randomly, right? So when you in the world, right, when a molecule gets into a certain size, and they have a certain fingerprint associated with them, there is no way you can generate that molecule. So you don't even have to look for polymers, you just look for a molecule. For a chemist, it's very easy to look for a molecule. It's the same way when you're looking for the Higgs. The easiest thing for the physicist to do is to collide protons together and look for the Higgs boson to be created, or evidence of that in the trails. We could look for DNA starting to be made from scratch or the equivalent, but what we want to say is when we can find molecules that are so complex they couldn't be formed unless there was a process of history, information gathering, constraining, that's what we need to be able to do. And fortunately, we developed a technique to go and look for aliens, actually, in the solar system, or let's call it astrobiology, right? Alien sounds cool. It's like, find aliens, but it literally is that. And the way we'd find the aliens is in the molecular signatures. I'm having a lot of arguments with chemists because chemists think that complex molecules could randomly form. But it's like expecting one of these watches to form in dirt randomly. It can't happen. It won't happen. I mean, look, it's even lighting up at the back because it's going to measure my blood oxygen level and my heart rate. So I think that's the key, is the fact that we are looking for assembled motifs. Lego is equivalent to Lego blocks. And because the Lego blocks are compressed together in 3D, it's much more interesting than looking for a polymer.
But so what's the control then in these experiments?
Is you do the thing without recursion. So you just do the experiment, and you could do two things. You could do the experiment for a very long time without the recycling, just leave it going forever, or you can just have a background there, and then you just do in mass spec. You look for the increase in complexity. Does the molecular weight and the complexity of the molecules go up in my control versus recursion? And and look at the differences and what processes are going on in the recursive system versus the standalone system.
Mm-hmm. And how do you choose the seed? Is there sort of an? It sounds like there are a lot of choices. Where do you begin?
You don't choose the seed. The seed you just do. I just randomly choose it. Whatever you want. Moon rock from outside. I think what you have to, what I think is like saying, how do you choose the point at which you're going to fall to Earth, right? In a gravity well, to prove the existence of gravity. Gravity is everywhere. What I'm really excited about, what might actually, might confuse, annoy, or just get your viewers, listeners really excited, is I think that all matter leads to life.
So you would expect to find, if we go looking on Europa or Mars or somewhere, then you would expect to see life even in those extreme environments.
Well, let me put some limits on it. I would say potentially yes, but all matter, if you've got some energy and you can make and break bonds, if you have the ability to store memories in chemicals, a bit like on a photographic plate or by making or breaking bonds, then you will in the end get life. That's my conjecture. So you can't go and look on Mercury, it's too close to the sun, all molecules will be vaporized. You probably might not want to look on Europa because it might be a bit too cold, but there is evidence of water and there's evidence of warmth, so let's not be too, But on Venus, now Venus isn't alive with phosphine. That was a very strange declaration, but Venus might have life on it. Might have very interesting life on it. It's hot, there's stuff going on. So I think that what we need to do is be very careful about what limits we put. Right now we say we must look for habitable world. So habitable world is one that reminds us, like Earth, that you can have so what is a habitable zone? You need to have enough energy for liquid water, and perhaps you need to have the right gravitational force, right, to keep an atmosphere and all that stuff, right? It's not just gravitational force, you need a magnetosphere and things like that. That's why Mars presumably lost its atmosphere because it didn't have tectonic activity. There was no magnetosphere and just everything got scraped into space, I guess. But I think it's really simple. So I think that I just want to try and create a new life form in the lab. And if I do that, I can then start to basically tell NASA and anyone who wants to look for life in the solar system first and then elsewhere, how simple it is to look for life. Because looking at the problem we're doing right now is we're being far too prescriptive. It's like you saying, okay, you're wearing a very nice looking t-shirt there with these bicycles on it. You might say, only conscious beings wear these t-shirts. So that you could go around, I'm sure there's other people with that t-shirt, I don't know if it's bespoke, but if you go out, it's like looking at other t-shirt, people wearing their t-shirts, say, oh yeah, I found that t-shirt, definitely another conscious human being. So what NASA did for a while is say, oh, we're going to look for amino acids, or we're going to look for DNA, or we're going to look for RNA, or we're going to look for this. And I think that but these things can occur outside of biology. It is possible to make amino acids randomly. It is possible to make a DNA new base pair randomly. So if you find those, that's not the same thing as saying you found life. You need more. You need more complexity, more information, more evidence of an evolutionary history.
But would you expect to find these things in large quantities randomly?
Yeah. So that's the point. So that's So I think, Shane, that's a really important point that I often forget to say, because people get there confused and say, you want to find, a really complex molecule. And you give my watch an example, right? And I guess physicists get confused with probability. The physicists would say there is a finite probability this could assemble itself. I could show you with a little bit of mathematics that's impossible, right? It's impossible. But I think having that argument is actually is mute. That's not the thing. What you want to say is like, look, if I was to, let's just say that a random one is allowed, because that's okay. Let's just do that. Let's just meet the statisticians at their game. Say, if I find one of these, you're not that convinced. But if I find 10, 100, 1,000, and they're all functioning digital watches, you'll be like, oh, I can sell these. Someone made them. So that for the complex molecule argument, you need to be able to not just detect one, but many, many thousands. Fortunately, the experiment I'm using in the lab, mass spectrometry, doesn't just detect single molecules. You need tens of thousands of molecules, which is still not very many. If you in the scheme of your sample, well, there's countless trillions and trillions and trillions. Remember, 18 centimeters cubed of water has 1 mole of water. Okay, that's 6.022 times 10 to the 23 molecules. So that's a lot of molecules. So that's kind of cool. So you only need, I would say, 10,000 identical copies in a mass spec. Maybe a few hundred if you've got a really good machine or something. I need to go and do that calculation and ask an engineer to help me. But literally, it can't be random. It has to be an abundance.
So what has the outcome been of your experiment then? Are you finding these abundances? What has been done?
So we're doing these experiments. So first of all, we needed to validate our experiments in a life detection system, which we've just done. So we've shown that dead things produce low complexity things, and that living things produce high complexity things. And we've taken very complicated, people that think are complicated, like classic meteorite samples, like the Murchison meteorite. It's a very famous meteorite that landed, a very big meteorite, and they found literally hundreds of thousands, billions of if not trillions of organic molecules on the meteorite. And they were like, whoa, how do we know this has not got enough complexity to evidence life in the universe? And there is a complex mess, but that's not the same thing as having complex artifacts, which there are not, and we detected it. So we've basically calibrated our detection system. So we've done that. We found the anomaly on Earth, which is life, because you can look around at samples and go, dead. Well, what's that? Oh, that's the Earth. Good. And then what we've done is we've built the machine in the lab, and we're starting to kind of earnestly go through our controls and do the experiments. And we are seeing things, right? I haven't got a big smoking gun to say, oh, we've found a life form. But in some experiments, we've shown evidence that you can generate this complexity via replication, molecular replication. And in other experiments, we've shown that you start to get anomalies. You start to get a growth in complexity that you would not expect to get unless there was an information system in there. And because we're building that theory and trying to show that all that evolution is a chemical, is a history, if you like, that you can use to inform your future decisions. So living systems are basically different from dead systems because they can do a number of things. The first thing is that they can do something different in the future than they did in the past. Really important. Might sound obvious, but the rock in your garden or you find can't do anything different in the future than did in the past. It's just static. So living things make decisions. Okay? And those decisions are controlled by the environment, the interaction of the environment with the object and the object with the environment. And because the object has a memory of what happened before, if they see something changing in the environment, say the temperature is going up, the object might go, oh, temperature's going up. I've got a mechanism to basically preserve myself, to stop me from getting, destroyed. I will now spend resource building my defences, or things are getting cold, if you see what I mean. So basically, the only thing that life is, the meaning of life is basically the minimal kind of response to change in the environment, where you have a memory of how that environment has changed before, and that's pretty much it. Life isn't that interesting from that point of view. It generates all the interestingness as it goes through evolution. So we're seeing hints of that in all the experiments right now, but we've got to validate it, get it peer-reviewed. I've had a whole bunch of peer-reviewed papers which have proved the principle of environmental selection. Published that a few years ago, but we did those experiments by hand. And we had a fairly hard time convincing people that, this was the seed, right, of doing stuff. We've also got a bunch of experiments that show that inorganic molecules that aren't anywhere near as complex as DNA can self-replicate and make more complex entities that are able to replicate. So they're made of what's called a catalytic set, an autocatalytic set. That's really interesting because that gives a way of getting something of the order of complexity of DNA and RNA without the need for evolution, just getting from the physics of chemistry. Mm-hmm. And the other thing that we're seeing in our kind of Large Hadron Collider, CERN-like experiments, we're starting to see changes in complexity. And like I say, that's not peer-reviewed yet, and it's always worth saying. And so is that going to lead to life? I think so. Are people going to believe us? I doubt it. But, I think that let's see, and we might be surprised. I mean, I think that it's a very simple phenomenon we're searching for, and I think it's obvious that reality does this. And I mean, I think that the creation of life is as obvious as the creation of a gravity well and a meteor falling to Earth, because the gravity well drags it down. So we've just got to be really careful in doing the experiments and show the anomaly, and then let the world decide.
If life is inevitable, and perhaps it's inevitable in the form that we see it on Earth, since that's the one example we have, why would you go after different chemistry? I mean, if life in the current form is inevitable, then what makes it obvious to start with the particular seeds that... I mean, I take it from your experiments that you don't expect eventually to get to a cell.
So we are not necessarily doing different chemistry. We're not banning the chemistries present on Earth. We've got all the elements that life on Earth has in our experiments at different times. So that's carbon, nitrogen, oxygen, hydrogen, phosphorus, sulfur, chlorine, and some metals. But I think that may be not the first life form that came. I think that there might be other ways of doing it. I just don't know. I don't know what is the minimal unit or system that can competently evolve. And if there is just one, I think there might be zillions, and they all have common traits. But as they then share information and share contingency, that their numbers go down, and it's just a pyramid, and in the end there's a winner at the top. And that winner can get through the evolutionary glass ceiling. What is a glass?
I see. So you're just being a little bit agnostic.
Yeah, as agnostic as possible.
I see.
That distinguishes us from most other researchers, who most of them now are pretending to be agnostic, but they're really just pushing a particular chemistry.
I see. But so I was curious on the topic of holding information and DNA in particular. So that just out of curiosity, so when you look at how information is stored on a computer, we have our bits 0 and 1, but in DNA we have 4 bases, which seems like a bit of overkill. Especially since we could encode for like 60 or something, 64 amino acids, and we only use 20 or something like this in biological life. So is it? Do you think earlier life or more primitive life only used 2 bases, or did the chemistry itself sort of single out these 4 bases? So how did we end up with this? What did these 4 bases do for us? Was that inevitable?
So I think that once we'd started to embark on the carbon-nitrogen heterocycle stuff that we're looking at, I think the emergence of the 4 bases makes a lot of sense, but I'm not sure it's inevitable because I don't know what events happened. But there is a lot of molecular biologists, a lot of very good chemists who turn molecular biologists, have looked at this quartet and then looked at the error correction associated with producing amino acids and coding things in the machinery. And there seems to be some consensus that there is a good way where there is not only there's not only a kind of historical contingency there. Some things had to happen in the past, which meant that you couldn't really make it simpler in the future. But also you got benefits from correcting errors and making sure that you could have redundancy in the gene and the different mechanisms that would read it out. But I just don't know if any of those are really proven yet. I think the only way to do it is to basically ask yourself how many solutions are there. I would guess, and it would be a guess, that there's some numerical correlation. 4 is good. Why is 4 good? Well, let's look at the square. Let's look at the way the RNA transfers amino acids, into the ribosome, into the protein, that whole translational process. So there's something there. But I would also say that there's a lot of accidents that have gone along the way, and I think without questioning the assumptions made by the bioinformaticians and the prebiotic chemists, it's very difficult to know for sure. Could life be made without DNA? Right? Is DNA the molecule? Does it have to be a double helix to do these things? Does it have to be? That's really hard to say. DNA is a remarkable molecule. It's suffice to say unique in a way that you have this digital polymer, the only example of a digital polymer on Earth other than proteins, right? And RNA. And this is, why is it a digital polymer? Well, every site in that RNA was put in registry from in the process of replication. That's pretty phenomenal. You have 4 monomers, and then the 4 monomers go stick, and you zip it up. And that, chemists are nowhere near that elegance, in the laboratory. They can do it stepwise synthesis, but nowhere near that way. So kind of redundant organization. So I'm not really able to tell you too much right now. I could guess. I could go outside my expertise and say, certainly there's this, and I'm sure you can find bioinformaticians that would agree with me, and then some that would disagree with me. But I think, I don't know any limitations why you'd have to have 4 base pairs, and I don't know of any limitations why you have to have DNA other than on Earth. Look at it, it's a helix, it unravels, the process of assembling up to make the strand ready again to go, and then before it divides, is just really brilliant. But how much of that is just a model that I have in my head that was put in my head by going all the way back to Francis and Crick?
I guess the one thing I would guess, and
Sorry,
again,
what's in the Crick? Sorry, go on.
No. So I'm absolutely not a biologist or a chemist. But my guess, if I had to make one, would be that if you have 4 base pairs, then you can use 3 of those triplets to code for some amino acid. But if you only had 2, then you'd need a larger, you need 5 or something base pairs to encode for a given amino acid, and it might just be that the geometry of the chemistry you're trying to match to doesn't fit.
Yeah, but the thing is, you're looking back at that detective story as a deterministic. If you probably were limited to 2 base pairs, why would you choose amino acids that link in that way? Why would you go on a 1D polymer? Why not go 2D and then have different coordinates? It's very easy to kind of find a solution to the problem. I think, and I do agree with you. I think it's really alluring. It's nature's done something right. We're still here, and wouldn't it be fascinating if proof of life was literally, or proof of getting, doing enough to get to Stockholm is required, then really what you need to do is to independently evolve a totally new information storage and translation system that is not DNA based, and show that it works. That would be pretty awesome.
Yeah, it's just that from an information perspective, it seems like two base pairs would be the simplest. Like, jumping from no base pairs to four base pairs seems more difficult than jumping from 0 to 2.
Yeah, but I
And
think that again, you're looking within the framework of what we already know, and I don't think that. I think the problem we have suffered from life as observers is we're trying to recreate what we know now, and like you say about it's like the whole artificial intelligence and what came before it. I think that your argument is interesting, but it doesn't help me do the origins experiment. Because when I put in the four base pairs, I've got four pieces of information to account for. Where did that come from? And then how did replication get invented? And there's all these other bits. So all I know is there's a phenomenon I'm looking for, and that's evolution. I've got a metric for it. Okay, I've got a detection system for it, and I have a machine to make. And I'm going to go and look at how well can chemistry evolve without existing biology, and that is the question. And how do we what is the leap we need to take from minimal non-evolving chemistry to evolving chemistry to biology?
So I know that you prefer to talk about what can be done today, but I was hoping also just to ask you sort of your imagination for the sequences of events that actually did occur. If you were a betting or a guessing man, did life begin with RNA? Did it, if you had to make this guess,
I couldn't guess. I mean, the thing is, I would say that life needs bonds. That would be as much as I would be willing to say. Life needs bonds and molecules to interact in networks, and at some point, life used those bonds and molecules to make, and there was some concatenation going on, some catenation, some linkaging, some formation of chains. And that was the route to life. But no, I mean, the RNA world is like a fanciful dream, because of the RNA world. The reason why I'm not saying that RNA was needed is because the information required to generate the RNA world is huge, and then you're then stuck with, where did the RNA world come from? And everyone says, it's just in synthetic chemistry. Well, what I'm about to reveal in the next few weeks, and I can't really explain to you right now, is I can prove that's just not true. I can prove that basically the RNA world is the equivalent of waiting for a Tesla to assemble itself and just form in your backyard. Okay, I mean it's a dramatic example of it, but it's the same problem.
I see. So you don't want to give any more hints towards what that proof is?
Yeah. So what I can. It's a little bit like this. I'll give you a little bit of a hint. So. I don't know if you like to play poker or bet, but if your grasp of statistics. But if I say to you, the RNA world requires the equivalent of me taking a coin and taking a coin that has access to heads and tails, and if you flick a coin, right, and I only give you say 100 flicks, do you know what's the distribution going to be like of getting maximum number of heads or tails in a row is?
No, not off the top of my head.
I mean, if you think about it, it's probably going to be. If you think about it, if you do the first one, it's a half, and the next one is a quarter, and it keeps going down and down and down and down and down. So you're going to get you might get a few where you might get a population of 6 heads in a row, maybe 7, maybe 8 if you're at a absolute, But really, you're just going to get a few, right? Now, the RNA world requires the molecular space to get about 30 heads in a row perfectly from 30. And so what I'm showing is that the chemistry behind that doesn't allow that to happen. It's just impossible. So what that effectively means is that there is an upper limit on the amount of information that we can get for free from chemistry, and it's very limited. And so that there needed to be below the RNA world another living system that basically was able to undergo evolution. And it's not evident to me that living system went through an RNA world. It's like saying, whoa, I've seen my BMW or my Audi and like it's got doors and wheels and engine. There must have been a world where engines were just wandering around on wheels because we see the engine as part of the car. And it's like...
I see.
No.
So it's a statistical argument based off certain assumptions.
Yes, well, the assumption that chemistry is not magic. And again, like people think that some molecules are predestined to happen. That's not true. There is no little rule book on the bonds between the atoms and in the quantum laws saying you will form this molecule and not this molecule. It doesn't. It's not right. What it does say is that some molecules are more stable than others, but the space of stable molecules and the space of unstable molecules is still vast. So when people start to say, oh, I think I can imagine this molecule being selected, you go, aye, selected. Right, now we're getting somewhere. What from? So I think there is a really nuanced statistical argument to say the chemists kind of think that you can get some complexity for free, and I'm just trying to explain to them that that is not true. It breaks the second law of thermodynamics, and it breaks statistics. And, you know...
even with a big energy source.
Yeah, sure. I mean, you can flick a lot of coins at once, but you're not gonna get 100 heads in a row. And I mean perfectly, right? Perfectly. Otherwise, you get a different one. You just write down a number of constraints.
So the I guess the image is though if it happened to be the case that back to your poker. Is it poker where you have flushes? I don't play cards. But anyway, so let's say for example when you get a particular hand that increases the chance of getting some other hand. This is back to the picture. So some questions outside of the beginning of life. So there are some steps in the process that, you know, we're multicellular, for example. So has beyond constructing single cell organisms, have people in the lab been able to start with single cell organisms and then construct multicellular organisms?
I think that it's hard to understand how that can happen I don't think it is possible to do, and people have tried to make organoids and things, right? But these cells have already been pre-programmed to make multicellular things, right? So the question is, what do you do to your cell to program it to become multicellular? Now, people are obsessed with the fact that we have this transition from kind of one type of cell to the other, from prokaryotes to eukaryotes, and the transition to that is you have to have your DNA in a nucleus, and you have to have your mitochondria and all this stuff, and then you've got this transition to multicellularity and then to intelligence, and the current evidence says that life on Earth was dumb for a very long time, and then suddenly became multicellular, and then ultimately intelligent. We don't know that's the truth. We just know in the fossil record we haven't seen any evidence of multicellularity in animals till relatively late. Now that could be for a number of reasons. It could be that the Earth is actually a non-typical planet in terms of its chemistry and the environment, or not non-typical. Sorry, let's forget that for a second. I don't know what I'm talking about. I'm tired. What I mean is that on Earth, the current conditions with the gravitational constant, let's say the mass of the Earth, the distance to the sun, and the lack of oxygen in the atmosphere, meant that biology had to invent, for intelligence you need movement. Intelligence is problem solving. Intelligence is nothing other than problem solving, right? I know we create lots of problems for ourselves. Life needs intelligence to problem solve. You need to move around to problem solve. And life didn't have access to enough energy to move around for a very long time. So I think the reason why Earth wasn't intelligent for a very long time is it just didn't have access to that energy source. That doesn't mean to say that intelligent life isn't a lot easier in other bits of the universe. So as soon as you have locomotion and you're able to make decisions, intelligence is needed.
I see. So in terms of the so those are two numbers you could add into the Drake equation. So the origin of life and multicellular life, which of those numbers is larger in your estimation?
I have no idea. I mean, I wrote a paper once on the origin of life Drake equation, and Sarah Seeger's written a modification to the Drake equation for looking for habitable life, or habitable planets, sorry. And the Drake equation is just a statistical formulation, right, of our uncertainty. And the problem is, because we only have one point, it's like you saying, here you go, Lee, here's a coin, flick it. I flick it, and I get heads. You're like, right, tell me, without flicking the coin again, what's the probability you're going to do that? I'm like, no, I'm flick the coin, you could have weighted it. So I think that's a very hard question to answer in general. And it's not that I won't answer it; it's just I don't know. And I really like making the habit of saying I don't know because, but I want to find out. I love being dumb, and then I do experiments to reduce my uncertainty. That's what we need to do.
So another question, sort of akin to the, similar to the multicellular question is, so from what I understand, I'm not a biologist, but from what I understand, our cells, each one has mitochondria inside of it, and this is, I've been told, these have been absorbed from some other life form early on in the history of our species. So can we think of ourselves as sort of a hybrid species constructed from multiple different species, or what's the best way of looking at that?
Again, until we have other life forms that have done this, we're not going to really know. But I would say that we are obviously hybrids. We're hybrids at the molecular level, at the cellular level, at the informational level. And I think that the mitochondrial kind of accident was fantastic for life on Earth. It allowed us to develop an entirely new technology. So I think biology likes taxonomy. And taxonomy allows you to kind of make sense of things and then put in a hierarchy. And obviously we need to do that to make sense of the world and categorize things. Is it useful to have that taxonomy? Yeah, sure. But if you use a taxonomy to then prevent you doing experiments about other things that could have happened, then that becomes a limiting feature, doesn't it? And so I think what we have to do, what my job is to say, okay, I'm interested on how we get to the cells here with these features. We don't rule anything in, we don't rule anything out, we just try the experiments. There is so much to be learned of that Genesis experiment, right? Getting to a first competent cell. Lots of people all stumble. They say, the origin of life is a fantastically hard problem because the cell is so complex. And that's true. But the cell, once it's established, is trivial, right? Well, trivial if you're using it and copying it in the context of biology. Really impossible if you're Craig Venter and some synthetic biologist trying to work out what it is right now that allows you to turn that cell on and off and replicate it. So I think what we try to do, or what we should all try to do, is to not worry about using current biology to limit our experiments and the way we go for the search for life. We don't even really know what life is. If you've got 100 of my colleagues together and say, what is life? Everyone would have a different answer, which would probably reflect their own bias, in their own journey. And I think it's a fascinating area. Many people have arguments about what life is or isn't. And that reflects a very personal quest that a lot of scientists have and a lot of human beings have to say, why am I here? What is the meaning of life? Hell, while we're at it, what is life? So it's not that I'm raging against the chemists. I'm just trying to calibrate everyone and say, well, we don't really know, do we? We have lots of interesting stories where to tell ourselves. Those stories are really useful in terms of developing technologies with existing biology, but maybe we can do a little bit better than that and actually use our naivety more constructively to come up with a way of finding life in the lab. Because look, if I can come up with a way with my colleagues and we can make life in the lab and we can demonstrate to people that life in the lab is possible from scratch, from sand to cells, then we can put the limits on where life is likely to, or not limits, right? Well, then we can free our mind and say, well, we don't need to look just for water. Maybe we look for this type of planet, this type of planet. Mm-hmm. Then we can start to look for evidence for life in the solar system. There must be some hint of life elsewhere in the solar system. And if not, why not? And then that might then tell us something about our experiments on Earth, and then obviously we can ask the question that we're all interested in, is there intelligence anywhere? And even with that intelligence, would be able to interface with it. I think on some level plants are really intelligent, very conscious. But they're not conscious at the point where they can appreciate, a discussion about a podcast or a Zoomcast or whatever. But they're relatively conscious. And that means they're able to make decisions and think about the environment. The thoughts are nothing that we could ever experience. And electrons aren't conscious, right? Only things in biology are conscious. And so I think, there's a lot of deep philosophy that comes together with all of this. And so it's no wonder that many people have struggled with the concepts. And all I'm trying to do is basically say, where's the anomaly? We're the anomaly. Biology's the anomaly. What's the experiment? What's the model? Let's try and recreate the anomaly.
Well, I thought what would be nice is to wrap up by asking you about, just the direction that you say the trajectory for the next 5-10 years, say, of your experiments. What are you hoping to achieve in 10 years when you look back and you're going to be proud of some certain accomplishments?
I hate doing this because I said in a TED talk many years ago, and people criticised me for that. I gave a TED Global talk, I think in 2011, 2012, something like that.
Mm-hmm.
And Chris Anderson said to me, and I gave it on Inorganic Life, and said, he said, and I said, I'm going to make a life form. He said, well, when are you going to have this done? And I said, well, within a couple of years. And he was like, wow. And we're now like 8, 9, 10 years on. And what I actually...
But that's how you get funding.
Well, no, I didn't do it for funding. And so I will restate that again, is once I understand how to set up the conditions, I think... So I partly said it to provoke people and get people to think that I genuinely think that the idea is testable in the lab now. So that was important. But also what I was trying to say is that once we've sorted out how to get the technology to work, we should take a few years to basically make the measurements and confirm that we can do it. It's a bit like the Higgs boson. 50 years to discover it, right? And actually, CERN wasn't set up just to get the Higgs. It was CERN, but it was set up to look at the standard model, look beyond the standard model, understand how things worked in the universe. And, it's an evolution of a bigger experiment. Take gravity waves. The idea of gravity waves was conceived by Einstein in maybe 1915, 1980, between that time, and then almost 100 years later, we detect gravity waves. But to detect gravity waves, we had to basically have very good computational models, otherwise we wouldn't know what we're looking at, and we had to have incredible technology, right? Really incredible technology. So what I'm saying, and then it just took a little wee while to, once the technology was up and running, I think less than a decade, to do it, actually. I'd have to look. So what I'm hopeful for is that in the next year that we'll have our evolutionary engines up and running. In another project in my group, I built the computer. And the computer is an engine that we can program to do all of organic chemistry. And when I set that out to do that, people said it was impossible, you can't do it, it's silly. But I only built the computer to make an artificial life origin of life system. I never designed a computer to make drugs. It just turned out when I was building the hardware, I was like, organic chemistry is like this. I can program organic chemistry. And then I realized if I went to the funders and said, hey, taxpayer, do you want to know if aliens exist? Do you want to know what the origin of life is? They'd be like, not another one. Give me £10 million. Whereas I went, aha, hey, taxpayer, shall we discover drugs more efficiently? Shall we get chemists out of the lab, make them safe? Should we stop people being wasteful with some chemicals? Should we think more digitally? Blah, 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 blah. And come fast forward, get the computer, we get really highly trained people who can make molecules using code. Only this year has that hardware been ready. It's taken me a decade to invent it. A decade. Or actually not quite 8 years. It'll be a decade by the time it's up and running. Put it in the artificial life team, and just this week, we've now built the first 3 rigs, and they're going to be running relatively autonomously from February, March, April, COVID notwithstanding, and whatever else, the next apocalypse, 2021. So I would expect us to make really good progress in the next 18 months to about finding out what can we find. And then I think certainly what will happen is a number of things will happen. We'll see if we can get complexity or information generated in the process of evolution. And we'll start to be able to put limits on how much effort we have to do as a team and where we should make this collaborative, international. And so what will happen is we'll get some hints, we'll get some success. There will be no Nobel Prizes, sadly, but not for me, maybe for my postdocs and my collaborators. who are just geniuses in general. But we'll make progress, and we'll start an international effort, and we will start to redefine what life is, get a better idea. B, start to put the limits on how we can make new life forms and what are the kind of chemistries involved. And C, start to really explain the theory that goes from the theory of the world based in physics to the theory of the world that gives us biology, and show there's a disconnect there, and then start to unify that disconnection. And that should happen in the next 2 years. And within 5 years, we really should have a big international effort. I think humanity needs a big international effort to find the origin of life. If we're excited to find the Higgs boson and to see if black holes exist, gravity waves, I think that we need to come up with a competent theory as a test, and we need to go do it. We want to know why we're here, or how we got here. Why is a hard a question, because why is different to everybody. But I think if we can show that life is an inevitable consequence of existence, I'll say that again, because that's quite a profound statement, that life, biology, evolution, is an inevitable consequence of existence, the same way in our universe as it stands, the sun burning and exploding and turning into a black hole. Well, maybe, I don't know, our sun will, I don't know if it's big enough, but the stuff that we see happening is, seems to be, is well characterized. Physics is making us feel confident. If we can come up with an explanation that shows how life is expected to be everywhere in the universe, that might actually do something for humanity's psychology, actually. Or we might come to the conclusion that we're incredibly rare, incredibly precious, and we should stop messing around. Maybe that's good too, I don't know. It's up to you and the people listening, watching this to decide.
Escaped Sapiens.